Okay, I'll be grading your test soon. I can't wait to see how you did. We're going to kind of skip around for this next quiz. We're going to cover 6-2, 6-3, and then we're going to skip all the way to 10-1 and 10-2. And then we're going to have a quiz. After that, we'll be on the final stretch, and I believe all we have left to cover will be some Topic 12 lessons. Okay, so let's go ahead and take notes for 6-2. Entitle your notes 6-2 Exponential Functions. And we're going to do some graphing. We're going to use a table of values and graph the function f of x equals 2 to the x power. So you want to make a table of values. I'm going to put y. You can certainly put f of x here. And let's start off with the values -2, -1, 0, 1, and 2. Those always seem to be very handy. Do you remember the rules for negative exponents? Just reciprocal. So this is going to be 2 to the -2 power. Remember, that's the same thing as 1 over 2 to the +2 power, or 1/4. Okay, 2 to the -1 power. Remember, negative exponent means reciprocal. 1 over 2 to the +1 power, or 1/2. Anything to the 0 power is, hopefully you said 1. Okay, 2 to the first power and 2 to the second power. Now, yeah, you can absolutely do the powers on the calculator. You'll just get decimal responses. Like when I did 2 to the -2 power, you can definitely do 2 and then raise it to the -2 power, and it gives you 0.25. If I did 2 to the -1 power, remember the caret up here, this little caret thing, that's your power. And then -1 power, I get 0.5. So you can definitely do it that way. Sadly, though, you'll probably get to an Algebra 2 teacher that doesn't let you use a calculator, so especially if you're going to the public school. So make sure you know how to do negative exponents. Okay, now I'm ready to graph it. I notice all my y values are positive. I'm not only going up to about 4. 1, 2, 3, 4. And then from my x's, I have from -2 to +2. Okay, so -2 up about 1/4 of the way. -1 up halfway. 0 to the 1, 1 to the 2, and 2 to the 4. And I'm seeing something kind of interesting, so I think I'm going to go ahead and add 2 more points, -3 and +3, just to see if I can get a better idea of what's happening. So remember, 2 to the -3 power would be 1 over 2 to the +3, or 1/8. And then 2 to the +3 is just simply 8. So if I put those points in, let me extend my x-axis a little bit. I'm going to get a 1/8, which is almost on the axis. And for the 3, it's going to go 4, 5, 6. It's going to be way up here. This is an exponential function, and it's going to behave like that. It's never going to cross this axis, but it's going to get closer and closer and closer to it. When it approaches something but never quite crosses, that's called an asymptote. A-S-Y-M-P-T-O-T-E. And once again, an asymptote is where it almost touches, but never quite does. In this case, it almost touches this horizontal at 0, y equals 0. Now, if we look at our graph, our domain, remember the domain is the x's, really has no limitation. It can keep going forever in either direction. So the domain is all real numbers. Now, the range is never going to cross the y-axis. it's never going to equal the y-axis. It's always going to be greater than the 0, and it can continue going higher and higher and higher. Okay, kind of interesting. Pause the video if you need to catch up on that. If not, let's go ahead and try another one. Let's graph one that has a fraction. Let's do 1/2 to the x power. And I should have put a y in here, yeah, or an f of x. Again, let's make the table of values. -2, -1, 0, 1, 2, and maybe 3. So you're going to have 1/2 to the -2 power. Remember that a negative exponent is going to reciprocal it. So that's the same thing as 2/1 to the +2 power, or a 4. Now let's try that on the calculator just so that you can see that it is correct. You're going to have 1/2, which is 0.5, and I'm going to raise it to the -2 power and get 4. Okay, 1/2 raised to the -1 power is going to give a 2. Anything to the 0 power is 1. 1/2 to the first power, of course, is going to be itself, 1/2. And then 1/2 to the second power is going to be a quarter, or 0.25. And then 1/2 to the third power is going to be an eighth, or 0.125. Go ahead and graph that. Did you set your graph up like mine? Okay, let's see if your graph looked like mine. -2 to the fourth power, -1 to the second, 0 to the first, 1 is to the half. And I said to the power, I'm sorry, I actually mean it just gives. An x of 2 gives a y of a quarter. An x of 3 gives a y of an eighth. So it's kind of reversed of what we just did. Once again, it's going to approach the y and never quite touch. So it is going to have a asymptote of y. It approaches the horizontal y equals 0. No limitations on the x. That's the domain. The range is always going up from the 0. Y greater than 0. The first two questions on your homework today are going to be to identify the key features. What it means by the key features is pretty much just the asymptote, the domain, and the range. Asymptote, domain, and range. All right, now I'm going to take you to the book to show you something that's kind of neat, especially in light of the whole corona thing or the reasons that we are in quarantine. It's because the virus is spreading exponentially. In your book, I'm on page 225, and this is an example of a computer virus that's spreading. So the network administrator found this equation to model the number of viruses that spreads. Basically, they had one computer, and it got the virus and spread it to 5 computers. And then each of those spread it to 5 more computers. Again, that's what's happening with the coronavirus. One person will get it and spread it. I haven't checked lately, but it's called a naught factor for the coronavirus, and that tells about how many people every person spreads it to, and I believe it was right about 3. So for every person that got the coronavirus, they would spread it to 3 people, and then it just keeps going. Okay, so taking this, they made a chart. The first initial, remember initial value was 0, computer had the virus. X is the number of hours. Okay, 1 hour after he got the virus, that computer spread it to 5 more. 2 hours, each of those 5 had spread it to 5, and now 25 have the virus. Continuing on, they graphed it. Now, the question here says if there's about 1,000 computers on the network, about how many hours is it going to take the virus to spread? Well, I can look here. If they've got 1,000 computers, they're in this range here. somewhere between 625 computers and 3,000 computers. So I would make my best guess. I could do it 4.5, but I'm thinking it's probably going to be a little bit less. The guess that the book made was about 4.3, looking at the graph they made that estimate. And then they put this in the calculator and got 1012.91. Therefore, they used that as the answer. So they're saying it's going to take about 4.3 hours to spread to the network. Let's see if you can take a minute and use your calculator to figure out how long it's going to take 50,000 computers to get the virus. Why don't you pause the video while you mess around with that and see if you can get the answer. So as I was playing on the computer, I found 5 to the 6th power and 5 to the 7th power, being roughly 15,000 and 78,000. So the 50,000 computers is going to be in between. So my next guess was 5 to the 6.5 power. And that's still probably too small because that's 34,000. So I can go from there, maybe 5 to the 6.6 maybe? Let's try that. Ooh, that's still a little bit too small. How about 5 to the 6.7? That's pretty good. 5 to the 6.8? That's probably too high. So I would say an answer of 6.7 would be really good. Let's see if I can get in between those two and raise it to the 6.75 power. That's even better. That has me at 52,000 computers with the virus. Okay, I thought that was pretty interesting in light of what's going on in our world right now. All right, let's get back to the notes. I'm going to do a couple more graphs with you. They're going to have a term in the front. And the reason for that is the general form for an exponential function is going to be f of x equals a times b to the x power. A is going to be your initial amount. So if we go back to the ones we've already graphed, the initial amounts at 0 at the very start was 1, which is why we're not really multiplying by anything here, because 1 times anything is not going to change the answer. Okay. B is going to be your constant ratio. That's a terrible arrow. All right. And your constant ratio is what it's going up or down by, what it's being multiplied or divided by. So like back to example 1, if I took the half and multiplied it, a quarter, and multiplied it by 2, I got a half. A half times 2 is 1. 1 times 2 is 2. 2 times 2 is 4, etc. On this one, I'm dividing by 2. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is a half, etc. All right, example 3. This time our function is going to be 3 times 2 to the x. Let's do table of values. Okay, what's the initial amount? 3. So that means that this graph starts out at the 0 value on a 3. And let's think about it. That makes sense because this is 3 times 2 to the 0 power. Anything to the 0 power is 1, so this is just simply 3 times 1. Now, when you do these, make sure you always do your exponents first. Okay. We know that 2 to the negative 2 power, remember that was a quarter, so this is 3 times a quarter. 3 times a quarter is 3/4. All right, let's show you how to do it on the calculator. We're going to do 2 to the negative 2 power. See it on the calculator. Get that answer and then multiply it by 3. I get 0.75, which is 3/4. Okay. The graphing calculators do obey PEMDAS, so you could just put it in straight like you see it on the paper. We could do 3 times 2 and then raise 2 to the negative 1 power and get the next answer of 1.5 or 1.5. Okay, let's do this next one. Can you think about what this one's going to be though? This is 2 to the first, which is 2. 3 times 2 is 6. All right, let's work it through. 3 times 2 to the first power is 6. Can you see the pattern? 3/4 doubled, 1.5 doubled, 3 doubled, 6 doubled. Again, let's try it. 3 times 2 to the second power. All right, ready to make a quick graph. Did you pause it so you could graph it? All right, let me get mine finished. On the negative 2, I'm 3/4 of the way up. On the negative 1, I should be at the 1.5. On the 0, I should be at the 3, at the 1 to the 6, and 2 to the 12. There we go. All right, let's just do one more just to make sure you've got this before you start your homework. Example 4 is going to be 2, and then we'll do 1/2 to the x power. Okay, please pause the video and do this one on your own. Okay, did you get it right? Notice the initial value is 2. This fraction, as you might have noticed on example 2, makes it go down left to right. We'll learn tomorrow that it's a decay. Where on this one, that number in the front is larger than 1. It is a growth. It goes up. So your fractions are going to decay or go down, and your other numbers are going to be a growth and go up. Okay, the only other thing I want to bring to your attention is on page 228 of your book. It does give a nice little summary. Okay, you're going to see a couple of homework problems where they're going to give you the table and you're going to have to write the equation. So what you're going to need to do is look to see what it's multiplying or dividing by, or you can think of it as a multiplied by a fraction. Okay, you're going to get your initial value from the 0, and then you're going to write the equation. So like if I look at these right here on page 228, notice this one, is it a growth or is it a decay? Hopefully you said a decay because they're getting smaller. Notice they're dividing by 2, which of course is multiplying by a half. Okay, so this is going to be a 1/2 to the x power with an initial value of 4. So if you were going to write this exponential equation, you would have the 1/2 to the x power times your initial value of 4. Okay. Look at this one. Is it a growth or is it a decay? Hopefully you said it's a growth. It's doubling. Every time it's doubling. So that would be a 2 to the x power with an initial value of 3. So that function would be the growth of 2 to the x times the initial value of 3. We did it. We already graphed that one. Okay, take your time with this homework. Don't rush through it. It's not difficult, but it is a bit tricky.